Welcome. Today I thought I would talk about and show you some more force problems and talk about some, I don't know if I want to say common misconceptions, but maybe some common places of error for different types of problems. If you remember from last time, I showed you the problem-solving method from our OpenStax College textbook. Four parts, and I guess it depends on how precise here you want to be. Part one, definitely draw a sketch of the problem. Part two is actually multiple parts. So identify all the knowns and unknowns, draw a free body diagram. So that's really a more scientific version of the sketch. And in the free body diagram, the object in question is just a dot at the axis here, the crossing point of the two axes. Many of the vectors will either be on the x-axis or the y-axis, but some will not. So in order to really help solve the problem, you'll oftentimes need to resolve those into horizontal and vertical components. And instead of calling them horizontal and vertical, so horizontal and vertical are sort of the names that we think of using, but really we can make it a little bit more generic. And our first problem is going to be a bit more generic, where we have a coordinate system that is tilted, and we've actually looked into that before. With kinematics, it seems like you just overrun with formulas, so many different formulas. X equals x0 plus v0 xt plus 1/2 axt squared. V squared equals the initial squared plus 2a delta x, and a bunch of other ones as well. Here you really only have one formula, and it's the one that the magic finger is pointing to right now. Well, no, not that finger, the other finger. It's pointing to. And from that, you actually make your own formulas. So if you're a do-it-yourselfer, this is great because you get to work on making your own formulas. So you don't care what the man or the woman has written for you. You're doing your own formulas. You're sticking it to the man, sticking it to the woman. And then finally, check your answer. Is your answer reasonable? And we'll be practicing that as well. Not only checking an answer, but just checking the number, but seeing if an algebraic solution looks right as well. We investigated this problem the last time we were together. This time I just stole an image from the textbook. And hopefully I'm not breaking any copyright laws. It is an open source textbook, and I am doing this for my class which uses that textbook. But anyway, 50 kilogram skier goes down the side of a 100-meter high hill angled at 25 degrees. What is her speed at the bottom? So we've got our free body diagram here, and I actually should have copied this and made it a little bit larger. But you can see it pretty well here. We've got three main forces. The earth pulls the skier down, and that's straight down towards the center of the earth. If there was no hill, the skier would accelerate down towards the center of the earth until hitting something else, such as the flat ground. We have the earth, or the side of the hill, pushing the skier up. And notice it's not pushing the skier straight up, it's pushing the skier up at an angle perpendicular to the hill. And that's why it's called the normal force. This is a not very common use of the word normal. In this case, normal means perpendicular. And then finally we have the frictional force. And notice the frictional force is typically going to be either parallel or anti-parallel to the surface, so along the surface. And for a skier going downhill, friction is going to slow that skier down, so the friction opposes the motion. So for this person then, we want to look at the sum of the forces, or the net force. Oops, got the wrong pen here, just a second. The net force in the direction that is parallel to the hill. So what are those forces here? Well, we've got the frictional force, of course, and we have this component. So the hill is angled at 25 degrees. So that makes this angle also 25 degrees. So this component is the opposite. So this is going to be the weight times the sine of theta. And I'll just leave it as theta for now. Or you can also write that mg times the sine of theta. So if we look at that, we have, let's go back to black. So in the positive direction, if we consider left to be, so if we consider left here to be the positive direction, we've got, and that's the same direction as A. And let's actually look into that. What if we would have gone the other way? So mg sine theta minus F, and I gave us a value for the frictional force equals m times A. Okay, well you can say, what if we had said, so this is if we have the positive direction to the left. So let's make that a different color because that's a note. What if we had made the positive direction to the right? We can, I guess, we're not cave people, we can add the word the. So now we'd have negative mg sine theta plus F equals, and in this case, the acceleration is in the opposite direction, so we could actually say that's negative, and then if we multiply through by -1, we get mg sine theta plus F equals, oops, I'm sorry, minus F equals MA parallel. Ultimately, we could have not used a minus sign here, not recognized the direction. Let's say we didn't know what the direction of the acceleration was going to be. We could leave this negative sign. If we didn't know what the direction of the acceleration was going to be, we could leave that negative sign out, and then at the end, we would just get a negative for the acceleration, and then we'd recognize, oh, we said positive was to the right. We got a negative acceleration, which must mean the acceleration is to the left. And of course, it makes sense here that the acceleration is to the left, or left, yeah, leftish, looking at it this way, but definitely to the left when looking at that coordinate system. All right, so going back to this one, that means that A parallel equals mg sine theta minus F divided by m But we don't want acceleration, or that's not our target variable. Our target variable is actually her speed at the bottom. So we want v at the bottom of the hill. So we know, I guess we didn't say it, we'll just assume the skier starts from rest. So V0 equals 0. Doesn't matter the time of day, so T0 equals 0. And X0 we'll say equals 0. X, that's a bit of a tricky one here because we say that the hill is 100 meters high. So that means that this here is 100 meters. And if we look at our little triangle, I'll use a different color. We'll use blue. So here we have our h equals 100 meters. This is theta, and we want to know what delta x is. And we know that the sine of theta equals opposite over hypotenuse, so h over delta x. So delta x equals h over sine theta, and since x initial equals 0, then x equals h over sine theta. I should have made that black again. Oh well. All right, so we don't know t. We don't know v, but that's what we want to know. So ideally, we would like an equation that has that which we know, so we can figure out acceleration. We know what x is. We don't know what v is. So we do have the formula v squared equals v initial squared plus 2a delta x. And in this case, we know that v initial is equal to 0. So let's just plug in. So v squared is equal to 2 times a, which is mg sine theta minus f over m. So that's the a, and then delta x is h over sine theta, where h equals 100 meters. So if we plug in those numbers, actually I just got the answer, so I don't remember precisely, but to two significant digits, that's 1600 meters squared per second squared, which means that v, the magnitude of the velocity at the bottom, or the speed, is 40 meters per second. And that's roughly equal to about 90 miles per hour. So our big question here is, so are the units correct? We do end up with meters per second. I didn't chug through it, but if you want to do that, actually I can go back and do that. So the units are correct. We'll check that. But is the answer reasonable? So 90 miles an hour, that's pretty fast for a skier, but there are extreme skiers that would go that fast, so that's not outlandishly fast. So let's check this out here. I was just checking my notes, so I was looking away from the camera for a bit. So our answer, we got v squared. Let's just go with the v squared part. So the units of that should be meters squared per second squared. And what we got for an answer was let me go back to the proper order here. In my notes, I did it in a slightly different order. mg sine theta minus f over m, and then h over sine theta. So we've got mg, so we've got kilograms, meters per second, and sine theta has no units, minus newtons, which is kilograms, meters per second, divided by mass, which is kilograms. And out here we have meters. So the kilograms cancel. We've got meters per second times meters, so that's meters squared per second squared. And they match, so the units work out. And yeah, I mean, I made up these numbers, so you might say that's not super reasonable. 90 miles an hour is pretty fast, but it wasn't 900 miles an hour, and it wasn't 9/10 of a mile per hour. Both of those would be much less reasonable. So folks that are participating, any questions or comments on that? Soon the world will be watching. I've been converting these to MP4s, and they're a little bit easier to watch through the class, and then I also am putting them on YouTube as well. So hopefully I'll be competing with Iggy Azalea for number of views, although I'm not quite as fancy. All right. You might recognize this picture from the book. I wasn't very creative. I just thought this would be a good problem to go over. I changed it around a little bit. Here we have a firefighter. And that firefighter is looking to rescue someone. And when you're fighting a fire, you've got specialized equipment, but there's a lot of water around. And you know oftentimes when things are wet, they get slippery, right? That was a Bon Jovi album from the 80s, Slippery When Wet. So this firefighter's gloves are wet, and because of that, she can only exert a gripping force of about 40 pounds. It seems like a pretty big number, but most people can exert a gripping force a lot more than that. So if you can pick up with one hand a 40-pound bag of dog food, curl up your hand around that, I think most people could do that. That would be a 40-pound gripping force. We want to know, though, if in this situation she can rescue the hanging person. So you might read this and you might say to yourself, well, okay, I wonder what I wonder where I apply this 40 pounds here. So I just realized when I stole the book here, let's actually make up a mass. Yeah, so there's a number in the book for the mass of this woman right here, but we're going to make up a mass for this woman. Let's just say the hanging person. Let's take a look. What does she look like her mass is? We're going to say, so anybody watching want to venture a guess what the mass of that person is? Looks fairly slim. She's kicked off her shoes, so maybe she had really heavy clogs on. Well, the world has not participated in figuring out the mass of this person. Oh, here we've got someone 130 pounds. So that's a good guess. In terms of mass, so Amanda mentioned 130 pounds. So if the weight of a person, and this gives us a good opportunity, so let's say the weight of the person, that was not a very good of, is 130 pounds. And it just so happens, I remember this, that 1 kilogram equals 2.2 pounds. So if we figure that out, so 130 divided by 2.2, so 59 kilograms. So that woman has a mass of 59 kilograms. So we want to know if this firefighter can hang on to the rope, her end of the rope, that this person is hanging on to here. So what we really want to figure out, and I'll put this in a different color because this mass was kind of a parenthetical thought. So is T2, so there's T2. So is T2 less than 40 pounds? If it is, then the person is rescued. All right, that's a pretty ugly looking word, rescued, there. All right, so let's get rid of some of these arrows here that are just messing things up. And let's go to solving the problem. So first off, we want to draw a free body diagram. So let's have a set of axes here. So in this case, it makes sense to have our traditional x and y axis, not tilted like we had with the previous problem. Okay, so we've got 3 forces. We've got the gravitational pull of the Earth downward. So the part where she, and so if we go back actually to this here, one of the things that we noted here, the object is represented by a dot. So what is the object in this case? In this case, the object in question is really her hands. So that is what we are drawing right here. So what are the forces on her hands? So the Earth is pulling on her. It's really pulling on her center of mass, which is down by her hips. But we assume she's not Elastigirl, although that was a great movie, The Incredibles. But she's not Elastigirl, so she's not stretching or anything like that. So a pull on her hips is going to translate through her body, and that same pull will be on her arms. And when she's grabbing onto the rope, that will be the pull on this point of the rope right here. All right, and then we'll just call this theta 2. And then we've got T1, and they give us this angle is 15 degrees. So we can call that 15 degrees from that axis, or that's going to be equal to 15 degrees from here. So theta 1 equals 15 degrees, theta 2 equals 10 degrees, T1 is we don't know, T2 is we don't know, and we know her mass is equal to 59 kilograms. All right, so this is a problem here where this is a static problem. That means A sub x equals 0. And, oops, stray mark. A sub y equals 0. So what we've got here, we've got two tensions that we don't know. Luckily, we have two dimensions. We've got the y dimension and we've got the x dimension. So the storyline for this is so our plot write the net force equations for the x and the y directions. This will give you two equations and two unknowns. And then you can solve it like we've done numerous times before. So I'm running out of room here. Let's go to this right here. So let's look at the net force in the x direction equation. So in the x direction, we've got T2x, and we've got T1x. And normally I'd do this on the next screen, but I'll forget by the time I get there. So T1x is going to be equal to, we could also do the same thing up here. So this is also T1x, and this is the opposite. So that's going to be sine. So that's going to equal T1 sine theta 1. And this one is going to be, again, the opposite. T2x equals T2 sine theta 2. So T2 sine theta 2 equals T1 sine theta 1. So we can then relate T2 to T1. So T2 equals T1 sine theta 1 over sine theta 2. And since the sine of thetas don't have any units, then you can see this works out. So we can then do the net force in the y direction. And in this case, we end up with sorry, I goofed up. This one is going to be, so nobody caught that. So this is actually going to be, T2 is going to be the adjacent one, so this is going to be the cosine of theta 2. So that means that I need my moral conscience here to help me out. So cosine of theta 2, and that means that this, I'm actually surprised I don't make more mistakes here, trying to focus on the screen and writing somewhat legibly. All right, so folks watching, does that make sense now? Did I do it correctly? All right, I got the yep, so I'm very happy with that. Okay, so again, I apologize. I'm actually doing the different colors here. I'm trying to be a little bit more consistent with color usage. I think from now on, black's my main color, but for components, first choice of components is going to be red, and then if we have a different set, I'll go to green. So that's a little bit Christmassy as well. So here we have T2y, and here we have T1y. And I thought that writing the equation like I did before on this page would help me not goof up, but sure enough, I goofed up. So T1y, that's adjacent to the angle, so that is going to be cosine of theta 1. T2y is opposite, so that's going to be sine theta 2. And now we have the weight in there as well. So the up forces, we've got, go back to using black here. So we've got T1 cos theta 1 plus T2 sine theta 2 minus W, which is mg, and that is equal to 0 since AY equals 0. I actually skipped a step right here. I should have started by saying T2 cos theta 2 minus T1 sine theta 1 is equal to 0. But I jumped right to this step here. So I'm not sure if that's a good thing or not. All right, so we can plug in. So we know that T2 is T1 sine theta 1 over cosine theta 2. So we can plug so we've got T1 cos theta 1 plus T2, but that's equal to T1 sine theta 1 over cos theta 2 times sine theta 2. equals mg. So we can factor out a T1. We can do that over here. T1 is cos theta 1 plus sine theta 1 over cos. Keep forgetting that S in cos. Theta 2 times sine theta 2 equals mg. So T1 equals mg divided by cos theta 1 plus sine theta 1 over cos theta 2 times sine theta 2. And if you plug all that in, you get T1 equals, let's see here, I used a different mass before, and I didn't write that down in my notes very well, because I had some cursory notes. So if we plug that in, and if actually one of you folks watching wants to plug things in as well, we could see how that goes. So we got our mass was 59 kilograms. So we're going to actually get an answer for this. And then what we can do is plug in so now we can plug this answer into this equation right here. So if I would have been smart, instead of doing the T2 equals T1 bit, what I should have done, because I changed my problem around kind of at the last minute, what I should have done is I should have said T1 equals the other way around, T2 cos theta 2 divided by sine theta 1. So now I don't know if anybody's tested this out here. So 59 times 9.8 divided by, and then we've got that complex fraction here, cosine 15 plus all right, I got an answer that is wrong, but that's because I multiplied by something when I should have added. So somebody got 572, so we'll see if I got that as well, because the first time I got 13,000 something or other. Yes, I got the same thing. So 500, so the two significant digits. So we got 572. Yeah, so I get to three significant digits. I also got that. So that means that T2 equals 572 newtons times sine theta 1, so sine of 15 degrees divided by cosine of 10 degrees. That's not a very good looking 0. So the book used actually a more massive person. So this is a problem that I got from the book using the book's numbers. They got something different, so but they used a different mass person. So for T2, I got 150 newtons. And you can check me on that one. It looks like 156 with that poorly written 0. And I said that they can exert a gripping force of 40 pounds. It turns out that there's a relationship between pounds and newtons. So 1 pound is equal to 4.45 newtons. So if we take that answer divided by 4.45, we get 33.8 pounds. So yes, she can hold the rope. And save the person. All right, so that was a really good formula to kind of go through some of the algebra, and it also is a good lesson in planning ahead. I didn't actually plan ahead very well. I could have saved a step. I could have actually got the answer in this circle here had I solved for T2 first. So solve for T1 and then plugged it in. So this answer here is T2. All right, one more. And this actually is just to start an analysis from this week's lab. You're going to be building something called an Atwood's machine. And Atwood was, I believe, a 17th century scientist, and he used this device to actually slow down the effects of gravity. Because you know that if you take something massive and you drop it, so on camera here I take a ball, which is not super massive, but I drop it, it's going to be pulled to the earth, and its speed is going to change by 9.8 meters per second each second. So if you want to figure that out, if you want to time some things, if I just drop the ball, I'm just dropping the ball maybe a meter here. That's really hard to time it because you take your stopwatch, or especially if you have your phone, you push the button on your phone, push the stop button on your phone. Your reaction time is roughly the same as it takes for the ball to fall a meter. So what Atwood did is if he had two masses, here's a mass down here, here's a mass up here. And whichever is the larger mass is going to be accelerated towards the Earth, and it's actually going to be slowed down by pulling the other mass. So here's an example where we've got the mass on the right is descending, so it's moving downward. The mass on the left is ascending, so it's moving upward. So let's analyze that situation. So first off, let's draw the free body diagrams for each. So here's M1. And one thing that I like to do, I'm glad this diagram does this as well, notice that M1 is the lesser mass and 1 is a smaller number than 2. That just helps me remember things a little bit better. Okay, so since this one's going down, that's going to have a larger force. So this is F2. This is F1. And then the only other force acting on this is going to be the rope. So we've got the Earth pulling down. And we've got the rope pulling up. And if the rope does not stretch at all, and the pulley does not have a lot of friction, the tension throughout the rope, so this is the tension, so you've obviously heard that word before. So that tension is the same on both sides. And I purposely drew these forces different arrows, or drastically different arrow lengths, so you could easily see that my tension force is going to be the same for both, same length. And note that the tension force is smaller than F2, but larger than F1. So I'm just going to squeeze that over here. So T larger than F1, but T is smaller than F2. And that makes sense. That's why one of them is accelerating downward and one's accelerating upward. So if we're to sketch these free body diagrams, which we did, and then we're going to draw our force diagram, we only have forces in one direction, the up and down direction. So if we look at the net force, we're going to have T minus M1G, so that's just from this here, equals M1A1, and T minus M2G equals M2A2. I'm sorry, I kind of squished that in there. And I also made a really ugly looking G. Yeah, that time I made an exceptionally beautiful G to make up for it. Okay, so we've got two equations here and two unknowns. So if we want to find the acceleration, so our goal here is to find the acceleration of each block. So our goal here is to find the acceleration. So this time, since we want to find the acceleration, we're going to solve each of these equations for t and then plug one into the other, or actually set them equal to each other. We'll do that on the next one. So t equals m1 a1 plus m1 g, and also t equals m2 a2 plus m2 g. So that's just these two equations, and solving each of them for t. But now we need to look at the equations. So one of them, so object one is accelerating, so up, m2 is accelerating down. So those two accelerations are going to be opposite signs. So A1 and A2 will be the same magnitude, but opposite signs. So let me quickly check my notes here. So since M1 is going upwards, we'll set M1 equal to A, and this little triple equal sign, maybe you've seen that before, that just means is defined as. And A2 will be equal to negative A. So let's just set these two equations equal to each other. So M1 A1 plus M1 G equals M2 A2 plus M2 G. And now we're going to plug in the A value. So M1A plus M1G equals M2A2, that's going to be negative A. So negative M2A plus M2G. So let's get the A terms on the same side of the equation. So M1A plus M2A equals M2G minus M1G. So what I did was I added M2A to both sides, and then I subtracted M1G from both sides. So factor out the A and factor out the G. So A equals G, and then this weird fraction, M2 minus M1 over M2 plus M1. And if you remember back from our problem solving, this one. If you remember back from our problem solving, is the answer reasonable? Well, it's difficult for this one to figure out what is meant by reasonable for something algebraic. So to check our reasonableness, so let's check if reasonable. And I know we're just pushing the end of our time. I'll be done in probably 2 minutes. So the units, on one side we've got units of, so here we've got units of meters per second. Over here we've got units of meters per second times kilogram divided by kilogram. Well, of course those cancel out, so the units work out. Now let's look at an extreme example. What if M1 equals M2? Then we get A equals G. Well, M1 minus M2, if they're equal, we get 0 over M2 plus M1. So that, of course, equals 0. If they're equal to each other, that's just these two objects are equal. There's not going to be any acceleration. So that kind of makes sense. What if M2 is much, much larger than M1? So let's say M2 is 1,000 kilograms, M1 equals 1 kilogram. Well, then we're going to get A equals G. M2 minus M1, that's going to be 999. M2 plus M1, that's going to be 1,001 kilograms. So that is almost exactly equal to G. And that makes sense too. If M2, if this one is really, really large, then this other one's not going to be affecting the falling rate much at all. So if we would have got something that was different from this, so if we would have made some mistake, and what if we would have gotten actually, I'm going to go back, to the next page, which is not the next page. There's actually a page at the top for extra work. So what if we got A equal G, and in this case, M2 plus M1 on the top, M2 minus M1 on the bottom. Then, when M2 equals M1, we get the acceleration goes to infinity because we're dividing by 0, and that is, this can't be. I will put that in black. So checking limiting the limiting factors or common scenarios serves as a check. All right, so just to summarize, all these were equations that we used in kinematics, and this is really the only equation that we use. This is sort of a subset of it for dynamics. Sometimes we use them together. So in this problem, we started with a force equation, but then we went to a kinematics equation depending on what we wanted to do. Here we just used the force equation, and it was a statics problem because we had no acceleration. And then finally we did an algebraic solution, and we used the algebraic solution to check for reasonableness, which seems odd because there's no number, but we looked at two easy to check scenarios: masses equal, drastically different masses. Okay, questions from anybody who's watching? You can just verbalize them or type them into the chat box. We've got a no and a nope. All right. Well, if anybody who's watching does not fit into the no or nope camp, feel free to email me. Or if by some chance you watch the video on YouTube, you can just put a question in the comments, and then the rest of the world that's watching the video will answer it. So Iggy Azalea, without me watching hers, she'll watch my videos. She'll answer your physics questions. Thank you.